We talked about the computing a C% confidence interval for the true proportion as an estimate, like an interval estimate of what the proportion could be based on a sample. Then we went a step back and we said, wait a second, what should the sample size be to get a certain confidence level with a certain level of precision as measured by the margin of error, either knowing or not knowing the true proportion, using 5 or 50%, 0.5 or 50% for the proportion to calculate the sample size we should use. And then we left with a discussion of tests of significance or hypothesis testing on a proportion where we make an assumption about what it should be, and we look for any evidence against that assumption. What we did last class was tested this hypothesis against the alternative of I think we did P less than, right? It might be, so as an alternative, we tested if P is less than the hypothesized, that's what the little 0 here means, the null hypothesis, the hypothesized proportion. Now we could have done, used an alternative that was greater than or not equals. And we're going to do that, but we're going to do it using or looking for a different or conducting inference on a different parameter, and this time the population mean. Okay, so we're going to start there, and I'm going to look at an example of greater than and not equals in the alternative to show you there is a pattern here. And although for the test I'm going to focus on P mu with sigma known and mu with sigma unknown, you can do this for other parameters. And I have in the notes gone into looking at a parameter being like looking at two populations to see if the proportion, to test if a proportion is the same between two populations. And I'm not going to test you on that, but I have those notes in the in your lecture notes. The one thing we will do is look at what's called matched pairs t-test. That's the only other thing we're going to do for in terms of preparing for the exam. If you remember back in discussing our first module on designing experiments and surveys, in the experimental design part, we talked about matched pairs designs, and we're going to come full circle and actually learn how to test if in a matched pair you see a difference between the pair. Okay. All right, so let's get into this. We're going to now shift. You can notice the pattern is similar here, where inference on the population mean. So the population mean could be the score on a test. It could be weight. It could be height. Those could be the variables that we're interested in when we talk about the characteristic of the population and the mean of the population. So it's a different kind of variable, but notice the pattern is the same. I take the point estimate and I make an interval, 2 or 3 standard deviations from the mean, but I'm very precise, and I call this the Z star the critical value, whether it's going to be 2.36 or 3.1 or it's called the critical value, and it indicates how many standard deviations away I am to have C% of the observations. And then I have to have multiply by the standard deviation or the standard error. In this case, if I assume sigma is known, which is unrealistic, really, right? Because if I'm trying to estimate the population mean, why should I know the population standard deviation? Well, it could be the case that I've done this study many times, or others have, and they've confirmed that the standard deviation should be a certain number. But from the number 3 here in sampling distribution of the statistics, X bar has a distribution and its mean is the true mean, and its standard deviation is sigma over root n. And I prove this using rules of means and variances. Now we're going to use this result. This will be the standard deviation of X bar. So I'm using the same pattern to calculate the the confidence interval. All right, so let's start there and then we'll go through the others. Are there any questions right now? So I kind of, I have, like I say, this is like the largest set of notes. But I have all questions and answers provided here for you. Okay, so I have a lot of problems there you can practice with questions and answers, and I encourage you to do that. So here's just a summary on page 18 of what we're going to do. And I start here. So in the videos, you know, I repeat a lot that I say in the videos, but it's, I think, going through the videos and then having this discussion, or in the other order, I give you the intro and then you go into the videos. It's all reinforcing the same material, okay? All right, so I'm going to start here. 18. A simple random sample of size 100, that's my N, is taken of women in Canada in hopes of estimating the true average height, mu, of all women 18 years of age and older. The sample average is calculated to be 64 inches. I'm going to focus on 64 inches. The standard deviation of the actual height of women is known, that's a key word, to be 2 inches. So that is sigma. Calculate a 95% confidence interval for the true mean of women's heights. So we are going to use the point estimate plus or minus z star times sigma over root n. So we have X bar we have sigma and we have n. So what is z star? For 95% confidence, what is z star? What do we do? Let's remember what we do. Anyone?
Go to the table.
So you can go to the table. Which table?
The T table that has the C star in the end.
Right. So we go to the T table with the z star in the end, or we can calculate it ourselves, but we'll go to the T table because I've given it to you. Or you can go into Excel, right? And ask for, or anyway, how would you do it in Excel? We'll talk about that after. Okay, so 95%, 1.96. And what is that again? Let's remember what that is. That is the number of standard deviations I need to be away to have 95% in the middle. And that's what that's confirming. Okay, so let's go back to page 18. Page 19, 18, okay. So that's 1.96. I'm going to multiply, or sorry, add 64 plus 1.96. Sigma is 2 divided by square root. I have to be careful to make my 2's look like 2's, not C's. And n is 100 square root. Minus. So you should make that into an interval. You don't just leave it like that. Even though our first exercise with a confidence interval, it was just the point estimate plus or minus the margin of error where you multiply these. But in general, you want to make the interval. So calculating the interval, I have it on the next page. So this would be the margin of error. You plus and minus 64. And this is the interval you get. It's very precise, right? We went through the trouble, we gathered data, we used 2 standard deviations as a given, and we got a very precise interval that the average for all women 18 and over in Canada would be between 63.6 sorry, I sneezed, 63.6 and 64.4. If you want to do that together. So I take 1.96 times 0.2 and I can store it and take 64 minus, recall 1, and round it to 63.61. So my rounding rules here are just to simplify it. I don't keep all the decimal places, so just simplify. 63.61 and then 64 plus recall 1, 64.39. Okay. And the next question. Calculate the confidence interval that would be accurate 19 times out of 20. How do we answer that? This is actually another way to state question A. And this came into commonplace, in the last, anyway, since I started learning statistics, to say this makes more sense to like a layperson who maybe hasn't taken statistics or understands the idea of confidence interval. This is another way to understand it. So this confidence interval would contain the true mean 19 times out of 20. Well, what's 19 divided by 20?
55%.
It's just another way to say the same thing. So these are the same question said different ways. Okay. Questions? So we can go into C. So to calculate C, it's the same problem, but now I want a 99.7 confidence interval. What will that do? We have to go look that up in a table. We'll find it's not there, right? 99.7 is not on the table. 99.5 is, 99.8 is. So what do we do for 99.7? How do we find it? Do a mental math or let's make a sketch. So these numbers are familiar because we talked that would be 3 standard deviations from the mean, but we want to be, that's rounding to 1 decimal place. You want to be more precise. So we could just, to find the limits, we could put this in Excel, this number 0.0015, to find out what the critical limit is, the critical level, critical value. So we can just use this function in Excel and put in the probability of 0.0015, and it'll tell us. Or it would be negative 2.97. Or if you want to have 3 decimal places, negative 2.968. Otherwise, you can go to the table, back to the t-table, and do the same thing. Look on the left side for 0.0015. So this is the left side, 0.0015 will put you up here. And we say, well, if they're the same, we just go halfway between them, right? If they're the same or evenly different from the number I'm looking for, 0.0015, I go halfway. So this tells me it's negative 2.865. So it's a little bit off again because this is rounding to 4 decimal places and you're operating with 4 decimal places. Now, the reason why I don't average these, I hope it's clear. I mean, there's not a clear, you don't average these, okay? That's not gonna give you, maybe it'll give you something close, but. So whether you want to use negative 2.968 from Excel, or that would be the more precise, but using the tables, because all of my notes were done using the tables, I probably have in the notes negative 2.965. The Z table result. So what did I use in the end? Oh, I don't have the answer. I usually have the answers. Oh, it's here. So I stuck with the table result. So 2 point, so it's almost 3. You see, if you rounded it to 1 decimal place, it would round to 3. But if you're more precise and you have more decimal places, it's 2.965 from the C table. And so what does this do to the value? Well, this is going to make a wider interval. We discussed that. So it's more likely to contain the true mean. However, it's a broader interval. And it's not that much broader, but we don't want to just make 100% confidence intervals, right? The convention is to make 95% confidence intervals. We don't need them to be 100% confidence because then they might just be too wide and meaningless in the end, because what we're saying when we present a confidence interval is all these numbers are similar and we expect our true mean to lie in there 100% of the time. In this case, 99.7% of the time. So just a point on confidence intervals just to illustrate. So I've done this kind of illustration before. Think about drawing a simple random sample. You would have these observations, and then you could calculate a mean, a sample mean from that sample. And you can simulate, so that would be a statistic, right, from the sample, but also the confidence interval is a statistic from the sample. I'm taking the sample mean and I'm adding this bit. Now, if I had another sample, all that changes is the sample mean, like it repositions the interval, but the interval width is the same, right? Because the margin of error is the same each time. If I use the same confidence interval, the margin of error is the same each time. So for a Z% confidence interval with that width, maybe this one will have, it'll have the same width, but it will have a different mean. Doesn't have to, but it could be different, is the point. Okay. And then you could have all possible samples, ... And the point is that 95%, theoretically 95%, or let's just say in general, the percent of all those intervals will contain the true mean. Okay. Any questions about that? So sigma is given, you don't control that. You can control as a researcher the sample size you want to use, and you can control the confidence interval or confidence level you want to achieve. Larger the confidence interval, the wider the interval. The higher the sample size, the more precise the interval. They work opposite. All right, so we're done with, let me position us. Okay, so we've done a discussion of this. The next column is sample size estimation. Now, if you wanted to know the right sample size to collect in order to get a certain level of confidence with a certain level of a certain margin of error, given a standard deviation, this is how you compute it. I call it, I don't know if you remember the Mazda commercials that were zoom, zoom. You don't have to memorize the formulas, but it's good to have a reminder in mnemonic device in your mind so you don't forget this square term here. Okay, you have to square, just like this one here. You have to square the M for Mazda, or it's really margin of error, but Helps you remember, you have to square this. You're going to get the wrong answer. Where does it come from? It comes from taking the margin of error here and setting it to m. And rather than computing m, we're going to take m as given and isolate n. So algebraically, that gives you this amount. I can show you. I'm going to cross multiply. You see? And that's why I have to square both sides to solve for n. So let's apply that. And remember, we have to round all the way up. And what that means. Okay, I put a few exercises here. So for the above question with n of 100 and the mean of 60, sample mean of 64, and given standard deviation of 2, what is the sample size n? So we use the formula. Since this is the formula, looking at this, so here we have confidence level 99.7%, practically 100%. But a margin of error of 1, using sigma of 2, you can easily calculate the sample size. Now, without getting the number right off the bat, if you use the same confidence level, but use a larger margin of error, what happens to your sample size? Is it higher or lower than A? It's going to be lower. So you don't need so much precision, so you don't need so much data. Okay. You don't need so much precision. You're allowing a margin of error of 2. So then you don't need such a high sample size. What about C? So in C, is it larger or smaller? And then A, if we have the same margin, but a lower confidence level. I don't need to be as confident. So M, I'm going to compare A. So, and the confidence level goes down, what happens to N? Not larger. So M is the same. All I've changed is the Z. Oh, I should make it a star. And I've made Z go down. So it's going to be a smaller number of standard deviations, so it's going to be smaller. In both cases. Okay, so less precision or less confidence, less of a sample size. You don't have to be so rigorous. Okay, so in summary, well, I do the calculations later, but I would want to make you think a little. The size of the simple random sample necessary for a C% confidence interval within a margin of error M is given by this amount. So now let's look at the calculations. So this is the highest, right? 36 women for greater precision and greater confidence. You're gonna need a sample of most women, 36 women. In this case, we allow a larger margin of error, so we only need 9 women. And this one, we allow not a larger margin of error, but less confidence, and so it's only 16 women. So notice the numbers, 35.16 rounds all the way up. To 36. Even though in general rounding, you would just make that 35. And we do that to maintain the margin of error of 1. This one will round to 9, and this again will round all the way up. So we already had this discussion here. Okay, any questions? I'm going to start tests of significance. So don't forget the square, maybe make a few calculations. Make sure you can get the same answers as me. Okay. All right, so let's look at significance testing. And first exercise is this one. So it's known that men between ages 35 and 44 have a systolic blood pressure that is normally distributed with a mean of 128 and a standard deviation of 15. So what did we learn? We learned that X systolic blood pressure for men 35 to 44 is normally distributed with a mean of 128 and a standard deviation of 15. So this is our sigma, and this is what? Our mu. So these are known. However, we're curious about a population of executives, male executives in the same age range, are they different? That's what we're going to explore. So in other words, we're going to use the status quo number, 128, but then hypothesize or look for evidence that, well, we're going to hypothesize that male executives have the same systolic blood pressure, but then look for evidence that it isn't the same, that it's different. Now, I don't know if it's higher or lower. I guess presumably we'd think it would be higher because of the pressure, but we're just going to look for a difference. And here's the question, and why I'm doing difference is because it says here, is an executive's blood pressure different from the population of males? It says different. Not higher, not lower, just different. So I begin with my status quo belief, no difference, right? So the null here, this is the null hypothesis of no difference. Same as the status quo, or in other words, there's no difference from what we already know. Null or no. So let's go into our method, our 5-step process to solving this problem, okay? First, let me tell you the results of a sample that was taken of 72 male executives, and their sample mean was 126.07. Looking at this number and the hypothesized mean, do you think they're different? Is 126.07 different from 128? It's very close. Given the theory and our the fact that we're told that we know that it should be normally distributed, what we're going to check is in terms of the variability of this systolic blood pressure and how it's, it's distributed. We're going to see how many standard deviations difference this is. It's probably not too much. Okay, so we're going to check. We're going to verify. You can do mental math. You can tell yourself right off the bat, is it an outlier? Is it? So that's what we're going to check. All right, so let's do the 5 steps and then recap. So as always in hypothesis testing, I put my parameter here, here, and always an equal sign here. All that changes is the number that I put here, and whatever number I put here, I also have to put in the alternative. Whatever I put in the null, I have to use the same number in the alternative. And then I get to decide if I put a greater, less, or not equals in that spot. So in this problem, what is the number that I put here? So before we used a P, now we're using the true mean or mu. Uh-oh, I'm getting out. What was the number that I put in the blue box?
8.
How much?
128, the average.
So the hypothesized mean is 128. I put it here and I put it here. And what symbol do I put in here?
Not equal.
And in here I put well not equals because
we just want to know if it's different, not if it's
want to know if it's different. We're not going to test if it's higher or lower. Okay, so this is the null hypothesis. Is the status quo or no difference from the status quo? And here we have the alternative that we believe to be true if we have evidence against the null. Okay, so that was our first step. The next step is A for assume. And we're going to assume that H, what am I saying? The population mean mu is equal to mu naught. So in other words, assume the null hypothesis is true for 128. And as a result, then, because we assume that X is normal with a mean equals 128 given a standard deviation of 15, then we know X bar is also the same shape with the same mean, but a narrower distribution, sigma over root n. All these numbers are on the other page. Let me grab them. I'll take them from here. Okay. That's the population standard deviation, the sample size. And so when I make this calculation here, 15 over square root of 72 is what? Nobody? So 1.77. What I get. All right, so I've assumed it to be true, and I get this result of expectations for the sample mean. So now I assess the evidence, A for assess the evidence. What's the evidence? So from the sample, from a sample, we have X bar equals 126.07. So what we do is find how different it is from 128. So we calculate Z, we call it a Z stat. It's a statistic. It's a number calculated from a sample. And it's equal to this is the kind of symbolizing I do. Just, I don't know if that is more confusing or what, but I need to take my sample result and standardize it, right? So that's, I can even write that as, so I write it in words, but I just want to be clear that it's the mean of X bar. So you go here, right? So it's the mean of X bar and the standard deviation of X bar. And if you don't have the true population mean, you have to use the standard error. We're going to talk about that next after this few exercises that we're going to do. So all I do is I take 126.07 and I minus the 128. And notice this is always for, because I assumed mu is mu zero, these are all from the hypothesis, right? This is from H0. And divide by 1.77. And that's my z-stat. And what do I get? So it's smaller, it's going to be negative. How many standard deviations smaller? So it's not an outlier, right? It's not that different. It's 1.09 standard deviations below. So we did not find evidence to refute the 128, but we want to put it into terms that, in terms of probabilities, as opposed to talking about standard deviations from the mean. Okay, so we're going to convert this and doing the next step called the p-value step, which is equal to the probability of seeing a z-stat as extreme or more extreme given H naught is true. So now I'm going to go and use the alternative to interpret that. So the z-stat as extreme or more extreme in the direction, well, this is saying in both directions. So what does that mean? So we draw a picture. Stand up, hold on. So what I'm drawing is I'm drawing the z-stat over here. And I'm checking as extreme or more extreme. So in other words, this on the left of the z-stat is as extreme or more extreme usually, but this time for not equals, I'm going to test on both sides because I'm going to see as extreme or more extreme in both directions. So to do both directions, I have to use the absolute values of the z-stat. I've got to go negatives, and this is what I have in my notes, which may be confusing, but this is basically how I resolve it using the drawing. So you put the positive of z-stat here, or the absolute values, and the negative absolute values of z-stat here, and you test on both sides as extreme or more extreme. In other words, higher or lower. So what's the chance of it being in the tail, in other words? of that. And we are in a Z stat, so this is a Z. So how do you figure that out? So what is the probability of being, what's the percentile for 1.09 negative? One, 379. So that's what you get from the table in terms of probability. So that's going to be the same on the left and the right. So in other words, the p-value is 2 times 0.1379. And I write it in symbols and I say 2 times the probability that Z, I think I did this, something like that, right? Or put the other way. So I want to check in the tails, in other words, positive and negative of the Z stat. Yeah, I think it's the right I wrote. Anyway, so you're going to go, so you don't have to write this out, just basically 2 times that. And that is going to give you the p-value. What does it mean? So what does this number mean? It means that the chance, so we found out that the result that we got is 1 standard deviation below what we expected. And that's not strange. So the chance of seeing a value that we saw, you know, so many standard deviations from the mean, the chance of seeing that was below or above that many standard deviations from the hypothesized mean is 27.58%. So the chance was 27.58%, or you could say 30, there was a 30% chance of seeing a Z stat like that. Is that unusual then? That we saw it? Is 30% chance of seeing it and seeing it strange? So how do we assess that? In the last step, the concluding step, we put it all together. We say, in conclusion, if the p-value, the chance of seeing that value was small, but we still saw it, then that's evidence against the null. So we are falsifying the assumption. We found evidence against the assumption because something very rare just happened, indicating that something's wrong with the assumption. So in our case, what is a small chance? We use the value. Do you remember? So if it's less than a 5% chance, then we would say we reject the null, but we didn't see that. This is not smaller than 5%. So we say we fail to reject H naught. We have not found significant evidence against the null. Where this thing is called is alpha, called the level of significance. And it's usually set to 5%. No idea why my font became so big. Okay, so we conclude the test is not significant. You say in sentence, there is insufficient evidence to suggest, oh, well, I'll just say it. There's insufficient evidence that male executives' blood pressure or systolic, there's insufficient evidence that male executive systolic blood pressure is different from males in general. So we didn't find evidence. We could do another test and keep testing, but that's what we found. Okay, so any questions about this process?
Professor, I have a question. I got confused in the p-value because I know that we're working with the absolute value, but we then again went into the C-score table and we got the negative value, the negative 1.09. So you mean when you mean the absolute value, it's gonna be the result. So you can enter in the negative chart.
So basically, so I did all that. You don't have to write all this. It's just some people like to see that. But basically what you do is you check above and below. So you check above and below in the tails. You don't go left and right of 1.09, right? You have to go in the tail. So you go negative, left of the negative one, and you go to the right of the positive one. So all I've done is I have to take this because when I do a difference, this could have been negative or positive. So that's why I have to do the absolute values, but then I can't lose the fact that I have to go left and right. So I do absolute values and go negative, absolute values and go positive because it was originally a negative. So anyway, just
Okay.
draw the picture and just remember you have to go in the tails, both sides.
Okay, is that I was looking at the C-score, but
For
they're
109.
positive?
You
Yeah.
you always have to look at the negative because the table only gives you the left side. If you looked at
Oh.
109, you would get all of this, and you don't want to get all this. You just want the left tail. So that's why you have to start with the negative.
Yeah, I'm just confused, and I know for the positive then
It's the same
you
number.
just
You don't have to look anything up.
okay, well that was the question. Well, thank you.
Yeah.
Okay.
Yeah, just copy over here. Oh, I'm gonna mess it up. Any other questions? So the next question I have, or the next thing I have to show you is when you do a test of difference, there's a faster way to solve this. And if anyone went ahead and worked through the notes on the videos, you would know how to do that. So, how would I do that? In a faster, rather than 5 steps, how can I do that quicker? No one got ahead? You can look in the notes. Okay, I'm going to take a 5-minute break. I have to check something, so you guys can look at that, all right? Let's take 5 minutes. Okay, I'm back. All right, so the question was, what's a faster way to do this when you have a test of difference? Anyone figure it out? So a faster way to do this, because what we're doing right now is testing to see if our test statistic falls outside or in the extremes beyond what's acceptable or what's considered acceptable. So we're looking at this drawing here and notice that we find ourselves here. What's between is the percentage of observations within one standard deviation from 1.09 standard deviations from the mean, right? This is like a confidence interval, but with a level of confidence, and that's basically what we come down to. Will this Z-stat fall within 95% confidence of the hypothesized, of the sample mean? Will the true mean fall within 95% of the observations around the sample mean? Will the hypothesized mean fall between? Okay, so that's what we're going to do, is like the opposite of this, rather than looking. So basically, let me show you what I'm talking about. I'm going to take this out. I'm going to take away these absolute values because I know they bother people, but I need to mention it because you see them in the notes if you're looking at the note. Basically, you want to go positive and negative, the number you get. So if we did reject, we would have been in over here. The blue, what's the total of the blues? What's the total of the blue areas? Okay, basically, if we were going to reject, we would have had to be in the blue area, but we're outside of the blue area. And to be in the blue area would have had to be for 5% on both sides. What would be the number of standard deviations to have 5% on both sides? Well, 5% on both sides is with 2.5% here. So how far would you have had to be? How many standard deviations to reject in a two-sided test? Can someone tell me? Well, I need more precision than 2, Gloria. I need you to go and look on the table and get me the precision. But yeah, it's about 2. So what you have to do is check for 0.0250. So you go onto the table. Oops. And look for 2.5% inside the table. 0.0250 is going to be this one exactly. Now what's this? Now this number should look familiar. 1.96. Now where did we see that number before? It was about 2, but to be precise, with more decimal places. So this is these mark where you have 5% in the tails. In other words, you have 95% in the middle. So that the level of significance and the level of confidence, they're complements of each other, okay? So when you're doing this for a 2-sided test, testing, building a confidence interval around your sample result and consider those values equivalent. And if the hypothesized mean falls in there, it means that percentage confidence, if you remember back over here, that's what I called it, C% confidence interval. So we're going to make a 95% confidence interval around X bar. So X bar was 126.07. So let's remember the formula for that. So it's 126.07 plus or minus. I'm going to make 95%. So this is 1.96. And then sigma was 15 divided by square root of 72, right? So what we're gonna check is to see if the true mean falls in there. If the true mean falls in there, that means that this value is not different from the true mean and we haven't found anything significant. Okay, so we're going to see if the true mean is no different from this value. I feel like I did something wrong. I missed the 1.96. What did I do? 15 divided by 72 equals times 1.96. Yeah, 3.46 is the margin. I just gonna round to 2 decimal places. So the convention is to use a 95% confidence level. So that's why I'm using a 95% confidence level. But Lucia asks why I got where I got 1.96 from. I looked up 2.5% inside the table to get 1.96 and realized that's just the 95% confidence limits, because if it's 5% in the tails, just look at the drawing, Patricia. Yeah, it's divided by 2. I just split it up. And it's 95% in the middle. So we're going to use this alternative method, make a 95% confidence interval, and we see. Okay, so let me give you some time to compute it. So these are all the values that are similar to 126.07 that you could present as a 95% confidence interval estimate. And since 128 falls in the interval, the test is not significant. In other words, there's no difference between 128 and the sample result. So we didn't falsify the null hypothesis. We didn't find evidence that 126 is just as good as, or just the same number as 128. So this is much faster. This is only possible for a two-sided test. Okay, so questions. Okay, so that's a test of difference for the mean. So what I changed was we're looking at a different parameter. So we're using a different sampling distribution, that one for the sample mean. But the process is pretty much the same, except this time it was for a difference. And because we did a difference, we looked in the tails on both sides. We didn't just look for what the probability was on one side. And then I showed you that you could do this faster for a two-sided test by just making a confidence interval around the true mean. And rather than looking in the tails to see if the 1.09 falls there, instead, we're going to see if the mean falls close to the sample mean falls close to the hypothesized mean, making a confidence interval to see if they fall together. And they do fall together in this case, so there's nothing different about them. So you would say the test is not significant, and the same conclusion. There's insufficient evidence that male executive systolic blood pressure is different from males in general. Okay, so we have an hour and a half to go. Any questions? So you can look at all that. There's also a right-sided test here, and you're going to do it like you did the left-sided test, except in the p-value step, you're going to calculate the probability in the right tail above. And I have a drawing here of it. All right, so I'll let you do that one. Then this one is about a decrease in salaries. I'll let you do that one. Maybe we can do that one together. What I want to show you is output. I want to do a problem with output because I could give you statistical output and you need to be able to interpret it. Okay, here. Okay, so this is page 35 of the notes. Okay, let's look at the statistical output on page 35 of the notes. Tell me what test we're doing here. So use the results here to like, so I don't have the question, I just have the results. What can you gather from these results on the highlighting? So let's see. It tells you here that this is a test for mean. So I know that this is a test for mean. What is the number that I put in the blue box? Right, so it tells you in words, right? Hypothesized values. That's the hypothesized value. So I'm going to put that here. 24.3 and 24.3. And then what sign am I going to put in the alternative? According to the highlighting. Right, it's greater than. So according to the highlighting, it's greater. Just going to put a red around it to remind you. Well, I'll just leave it like that for now. Okay, so now let's go through what we have here. We have the hypothesized value, so that is mu0. We have the actual estimate. What's that? X bar, right? It's going to be X bar. This is the actual estimate X bar, Marla. Thank you. And then you're told about degrees of freedom. So there's degrees of freedom 31. So that means N is how much? When N is 32, degrees of freedom, which is N minus 1, is 31. We're going to talk more about that when we get to doing the test when sigma is unknown, but they put it here. It's just output that generates. Okay, now they tell you this is S, the sample standard deviation, and they give you sigma 7.4. So this one is S, and this is sigma. So from this output, we should be able to carry out this test. That's the first step. This is the H step. The first, assume. So what we do is we assume X is distributed normal with a mean of, well, it doesn't even say that X is normal really, but the sample size is 32, so it's okay. It doesn't matter. Let's just, I mean, I should probably go back to the problem and see if I know if it's normal. Let's see. Let's go back. This is problem number 4. So notice it doesn't say anything about the sample coming from a normal population. So you cannot assume normality. What you're going to do though is rely on the fact that you have a sample size bigger than 25. So X is distributed with a mean of, so this is assume mu equals 24.3, which is our hypothesized mean. So then X is assumed to have a mean of 24.3 and a standard deviation. Notice I use sigma, not S, of 7.4. And this means because N is equal to 32 is greater than 25. Let me write that. This means that X bar is approximately normal with a mean of 24.3 and a standard deviation of 7.4 divided by square root of 32. See, I can get everything from stuff. So this is the central limit theorem that I use because I don't know that the sample comes from a normal distribution or anything like that. And now what do? I assess the evidence. Now, if I didn't make the assumption, I couldn't assess the evidence. So the second A is assess the evidence, which is X bar equals 27.75. So we calculate Z from that, the Z stat, and let's see if we get the number on the left side there. So we got to take X bar minus its mean divided by its standard deviation. What do you get? It's unbelievable. I have to learn how to, it's all relative. So if I make this bigger, it'll be smaller. See how that happened? Minus 24.3, which I got from up here. And then I get the standard deviation from here too. I can do all the calculation here, or I can do it in advance. I'll just do it in advance. But you obviously, if you do it in advance, you lose some decimal places. So I'll put the, and you'll see it in the notes as well. They just put it right in here, 7.4 divided by 32. Like that, and then you don't lose any decimal places. So I want to be precise like the computer was in giving that result. 27.75 minus 24.3 equals divided by brackets 7.4 divided by 32 square root close bracket equals. And I get the number 2.6373. Oh, but they say you did something wrong. Try again. Try again. Don't use the S standard deviation S. Use, oh, that was the standard deviation. Oh, thank you. Sorry. Okay, yes. So notice, even though I had the other information, I just used the sigma. So you're doing great there. You're helping me. I didn't notice. So that's my Z stat. We have all the answers. We have all the facts and the answers. So let's do the next step, the P step, p-value. How do we calculate the p-value? Draw a picture, and now we use this now, right? It says I want to go to the right of the z-stat. So I plot my z-stat. So I'll do 2.64. I want to go this way because of that arrow. I want to look on the right. I want to look if it's greater than. So is 24.3, sorry, is 27.75 greater than 24.3? It looks like it, but is it significantly greater? That's the issue. That's what we're trying to determine. So I plot my z-stat. Always plot your z-stat or your test statistic. And then, so you got to just be careful because the table only gives you the left side. So you're going to look up negative 2.64 to get this value. Well, I already know the answer. I already know the answer. It's going to be 0.0042. Because you want to go on the left side on the tables. That will be your p-value, small. All right. Any questions so far? So I've done all the steps. And let's conclude. Doesn't matter if you do a two-tailed or a left-tailed or a right-tailed that we're doing right now. You always use the same concluding step. So what did we get? So we always check if the p-value we got is smaller, if the chance of seeing a z-stack 2.64 standard deviations above the mean was 0.4%. Okay, so it's very small. So how small is small? Well, we're going to compare it to a 5% chance. We're going to say anything smaller than 5% chance, but it showed up, was not just by chance. That means something is strange. So it's not just a chance result. Something is really strange. So we do reject H naught. And we conclude, anyway, in this case, we just say the test is significant because I didn't talk about what the question was. We just looked at the numbers. So we've done a left-sided test, we've done a two-sided test, and we've done a right-sided test. And in this case, I don't even know what the question was in terms of the context or the storyline, but I can actually determine right from seeing this if the test is significant. So you find the p-value and you check it against 5%. And this is going to reject. So what does it say here? So this was about bridesmaids, oh no, brides, sorry, first-time brides. So since p-value is less than 5%, we reject the null hypothesis. At the 5% level of significance, we have sufficient evidence to conclude that the true mean age of first-time brides has increased over the past 25 years. That was the question. So you found something significant, something to report, something for the media to devour, right? You have some evidence that's worthy and significant. You rejected the status quo belief. Okay, any questions, comments? So we never used S. The output would give you S, but you don't use S in this case. Now, when will you use S? What is S all about? We're going to talk about that next. So let's recap. Okay, let me go back to our formula sheet that we're marking up. So we have done this now. Test of significance for the mean. Notice we don't know mu, so we hypothesize the mean here. And we standardize the evidence. The last line is the last material I will test you on. So let's do this. The difference between 5 and 6 is sigma not known. Now, as I explained before, I start with building the theory and then I make it very realistic and less abstract by saying, well, I don't know what the mean is, but I can collect a sample and estimate an interval that could capture the mean C% of the time. And I can also know what sample size is going to help me get a certain level of precision and a certain level of confidence. And I can conduct a hypothesis test, right? But what if sigma is not known? All of this was for sigma known. So what if sigma is not known? What's the best guess of sigma if I don't know sigma, if I don't know the true value of the standard deviation or the variance of a variable? The best guess that we have, the unbiased estimate, well, let's say the best guess is S, okay? So we're going to use S in place of sigma, but there's a price we pay, okay? Because it's not that easy just to substitute this estimate for this parameter. But in reality, we've got to do something because we're not just given sigma. It doesn't come down from heaven for us. So we're going to use S, but then we compensate by using a different distribution. And now I'm going to explain how the t-table works, because we have to use the t distribution instead of the z distribution. Now, the two of them are the same for large sample sizes. Okay, so that's why we were using the last row of that t-table, because for larger than 1,000 in sample size, the critical values and the distribution of t is pretty much z, the standard normal. Notice I don't have anything here in sample size estimation. We'll talk about that. And here again, all I do is substitute S for sigma, and I use T instead of Z because I had to substitute S for sigma. So it's the same formulas, but sigma unknown. All right, so let's talk about the t distribution. Okay, so tell me, what's the difference between T and Z? Let's make this a little more interactive. How many of you got that far or no in advance? There's a couple of things. It's a difference between T and Z, and then this table. This table is T does not represent the right tail, but the table shows you the right tail. Yes, you're right. So the T table is different from the Z table because it's giving you the right tail rather than the percentile on the left, right? Correct? So it always goes left for Z, so that's a good point. What about T? First, let's talk about T and Z. What's the difference between T and Z? So, and then we'll talk more about the table. So T is centered at 0, just like Z.
Profesora, yo leí que brinda un grado más de certeza a la hora de sacar muestras.
Okay, so T depends on the sample size. The T distribution depends on the sample size. So let's say a T of, let's look at a T here of 5. Let's do a T of 5. So this is a T distribution with 5 degrees of freedom. So you write it like T sub degrees of freedom, where degrees of freedom is equal to n minus 1. So let's do T of 4, so n is 5. Let's do it like that. So I'm going to do T of 4. So in this one, n is equal to 5. Okay, so there's 5 observations. This would be the distribution. 0 is always in the center. And then notice across the top here are the upper tail probabilities. And here are the critical values. So it's opposite to the Z table where I have the probabilities inside the table and the critical values or the scores on the margins, it's reversed. Okay, so here are the probabilities on the margin and here are the critical values. So I'm going to put down 6.314, and that corresponds to 5% in the tail. That's what that means. Okay, so that's 5% in the tail of 6.314. Oh, that's for degrees of freedom 1. Sorry, I got to use this one. So degrees of freedom 4 would be 2.132. So let me change that. It's better anyways. Okay, so 5% in the tail would be at 2.132 standard deviations from 0. All right, now let's go to a degrees of freedom of 40. Do we have that? Yeah, we do. Okay. So tell me, if we have a degrees of freedom of 40, where would you be for 5% in the tail? No, it's not gonna work. So just to show you, so let's see. So this column here, so for degrees of freedom of 40, 1.68 standard deviations from the center would put 5% in the tail. How is it possible with this drawing? Well, it's only possible if the whole shape changes, right? I think I made it too tight. Not the shape, like the shape, it squeezes together, narrows. Well, the first one was the best. Anyway, so if I go, let's do it here. So if I go 1.684 standard deviations, I'll do it in red. So it corresponds to the color picture. So in red, I have T40, 41 degrees, 41 is my sample size. And then (1.684) here in this, under the red is 5%, where this and the blue is 5%. Okay. So it's only possible if the shape changes. Okay, so it actually narrows and tightens. So what happens is, as the sample size goes up, degrees of freedom increases, the tails flatten. And the distribution is more peaked. Okay, so it becomes more peaked, and in the limit, the T distribution becomes a Z distribution, right? So this table gives you the upper tail probabilities. It gives you the right side only for the critical values, but you should be able to see the left side as well. If you want to go left, you just have to change these signs for critical values to negatives. So As opposed to in the standard normal table, you have hundreds of values of the z-score and hundreds of percentiles that accompany it, and you have positive and negative z-scores. Here you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 t-scores or t-critical values for each different distribution. That depends on the sample size. Okay. So you got to work with that. So I have some exercises where I review the t distribution. Here. Yeah. So I take some time to go through the differences and to talk about the notation. I can do a few of those and then solve a problem and then go. So this says find the probability. So these are back to thinking about calculating probabilities using the standard normal table. We're going to use now the t distribution. Find the probability of the right tail with t for t greater than 1.5 standard deviations above, right? So if n is 20, then degrees of freedom is 19. So you need to go to the 19th table. So I'm going to draw it first. And then there you go. And then I want to go to 1.5. And this is T19 to remind myself. What do you get? So we go to T19, which is down here. And there's no 1.5. So what do we do? I'm going to take this section of the table with me. Oh, why am I here? If you can hear my neighbors. Try that again. Finally, okay. So I don't have 1.5, but I do have this number and this number. One is for 5% and one is for 10%. So I can put 1.729. This is very messy. 1.729 corresponds to 5% on the right, and 1.328 corresponds to 10% on the right. So what I've done in the notes, yeah, you don't have to interpolate because you wouldn't know exactly the rule to use. So you can't interpolate. You'd have to, yeah. So my rules, you can't interpolate. It's just these numbers are not even, the shape isn't even. You can't just, yeah, interpolate, but that's a good suggestion. So what you're going to do is just say, it's between 5% and 10%, which if you're not happy, you can go into Excel and find it. So let's see, let's go into Excel and see if we can find the value. So let's go into Excel. Let's do this with split screen. And what I want to do, oh, so let's say I want to use a t distribution. So in Excel, t distribution. Now, which one should I use? Which function? Which formula? When I say we don't interpolate, because we're on a curve, right? We can't easily average or anything like that. Okay, yeah. So t dot dist. Let's see. Okay, so t dot dist. Now, is this going to give me the left or the right tail? So if I put in x of of 1.5, and I tell it degrees of freedom 19, and I say cumulative, what is it going to give me? So it's giving me the right, sorry, it's giving me the left side. So the Excel gives me the left side. Okay, it sticks with the rule of giving you percentiles. So you need to know that. That's why it's really important to know what you're doing, and use Excel as a tool. So this is going to give you the percentile, the left side. So you just have to do 1 minus if you use Excel. So the answer is 7.5%. That in my notes, using the table and just between 5 and 10 is good enough. But if you want to know, and you want to be a really good understanding, you want to test your understanding, it's 7.5% in Excel. And anyone want to see that again, or have the formula right there? So we're just doing the regular, hold on. Sorry. Okay. So, questions? 7.5%.
I have a question, Professor.
Mm.
So what we did in Excel, I know it gives you the left side opposed to what the chart actually gives you, right? Right? It's the right side.
Mhm.
Okay, so then the percent we just got, the 75, I just thought it was gonna be in between what we have in the table or something on that sort. It doesn't have to be like that, right?
Hold on, I want to just put the formula in that I made here. I'm gonna say 1 minus. Okay, so what was your question?
I just wanted to verify, so we got the 75%, so that's our answer.
7.5. 7.5.
Okay, but so I was thinking it was gonna be a number in between what we have in the table,
It is.
but it's not. Is
7.5
that
is between 5 and 10.
oh, okay, from the upper, okay. I was looking at the other numbers, the ones that were circled, so that was my doubt.
No,
Okay.
that's the critical value. We're looking at the probabilities on the top. Yeah.
Okay, thank you.
Okay. So yeah, we're going up. Those are the critical values, and then we went up here. So let's recap. So I put the numbers here because 1.5 is not on the table. So I use 1.328 and 1.729, which corresponds to 5 and 10%. And then I say that this 1.5 lies between 5 and 10%, but then I go into an Excel and get Excel. All right, let's try the next one. What would you say for the next one? It's the same sketch, but I'm going this way now. I'm going this way. So what's the answer? Yes, Marla, it's just going to be 1 minus 7.5, right? So let's put it in terms of the table and then in terms of Excel. In terms of the table, the answer would be between, so 1 minus 0.05 and 1 minus 10, between 95%, no, sorry, between 90% and 95%, or in Excel, that is 90. Why can't I do this? 92.5% in Excel. And again, my notes are based on the tables, but you can verify in Excel, or you can find the answers precisely in Excel. My goal and my philosophy is that you are able to do all of this with pen and paper and, a table. But in practice, you would be able to do this with Excel very easily. Okay, questions about that one? What about the next 4? Let's give you, let me give you some time to do these 2. Let's take, let me give you some time and then I'll do them. So try these. And then we'll do them and then we'll try the other 2. Did anybody get this far in their review? All right, let's do this one. So we're gonna go to T6. Let's draw it. I always draw it with a number in there, just so I don't forget what I'm doing. So T6, right? Because degrees of freedom equals n minus 1. And let's get the values for T6. So I'll clip that part of the table. All right, so what do we see? T6, and this is the right upper tail, right? So I don't see the number negative 1.44, but I do see the positive. So how do I deal with this? What I want is the probability that it's less than that's what I want, but I'm not going to get that directly off the table. I would get it in Excel, but not directly off the table. So what I'm going to do instead is draw it from the table on the right side where it's 1.44, and I know that corresponds to 10%. So what can I say about this? And this is because of symmetry. Symmetry in the t-table, like the z-table, right? Okay, so you can, even though you only have 12 critical values, you know the left side by symmetry. You just got to keep your head straight about what you're doing. Okay, so then what about T20? Let me move this, if I can, move this over here. Now I'm going to grab T20. Now this is a whole table I have to take. That didn't work. All right, so what's the question? The question was, let's draw it. So I'm going to draw it with T20. And I want to go to negative. Oh, this is not a very good drawing. Let me do that again. So let's say I want to go to 2.086 negative. But I don't have that on T20. So instead, I'm going to look at first the right side. You don't have to draw all the, you just got to know what you're doing, but I'm drawing it to illustrate what I'm thinking. Oh, I'm just going to copy this. It's easier. So 2.086, let's look at the table for T20. 2.086. Oh, well, it's miraculously there, right? So 2.086 is there. And it's 2.5, it corresponds to 2.5% in the upper tail. So that's 2.5%. So this has to be, by symmetry, is 2.5%. Okay. All right, so now do the last two questions.
Professor, I have a question because down below in the part of the solutions, you mentioned that the complementary event would be 97.5.
Oh, sorry, because I doing the wrong arrow. I did the wrong arrow. Thank you. Because I did this arrow. So from symmetry, this one, but the question wants the other side. Yeah, so I didn't do it right. So the question was to go right. So that's why I know this one is 1 minus 0.025. Thank you. And then this is 97.5%. I thought it was too easy because it's just like the other one. Yeah. So I want to go greater than. The other way to do it is just see that if I'm going to go, oh, just 2 minutes. So if I change the sign and the direction, that's the other point to make. So if I change the sign and the direction, I get the same answer. So this would be, the direction would be going left over here, which should give me the answer right away. So the steps in this would be, if you were to draw, so we begin by drawing, anyway, the whole thing is that it's a negative. So if you're comfortable with just doing this, this is the easiest way. So this requires you to change both. And sign and direction to get the same answer. So you could have done it like this and then just gone, use the table to get the positive and got the left side. And that would have been done. And then the other way would be just to see it over here on the negative side, but then do the same. You still have to work, you still have to work in the, with the table of positives. Sorry for the confusion. I missed the sign. All right, so then this last set of problems. So let's draw. So these are the reverse, these are the backward type problems, right? So I'm going to draw. And this is for T16. I'm going to shrink it because it's too big. All right, so for T16, you want to find the critical value with 0.5% or 0.005 on the right side. You want to find T. Now this is actually easy. Let's look at the table here, 16. All you have to do is now start at the top. So this is actually the inverse problem with the T table is easy because the probabilities, the right tails are on the margin up here. So you just gotta correspond 16 and 5, so 2.921. And the other one's easy too. So this is to end off on a high note that this is actually easier to do the inverse problem. Now, if you go the other way, but you change the degrees of freedom to 9, what changes? Let's draw it. So T9, where do I put my critical value? It says to the left of the critical value is a very small number. So even if you go on the table directly and you look that up, 9, and that number you get 3.25, but that's on the positive side. But we are looking over here. So it's negative. That's all because of the sign. Right. Okay, so you know how to use the T table. Or you have some practice. You have some practice. So what we're going to do before we go is look at for the same sorts of problems. The difference is that we don't have sigma. So it's more what people deal with on in a practical reality. In reality, we don't have a God-given sigma. We just have data like this. I'm on page 44. Oh, my pages got messed up because I added a bunch of pages. So page is 41. My page numbering down here does not reflect the real page number. So page 41, this is the data, and it represents the weight of a certain breed of dog, the weight of dogs of a certain breed. They're 3-year-old dogs, and we're going to assume X follows a normal distribution. So here is our sample. We're going to assume that both the true population mean mu and the population standard deviation are unknown, okay? So when that happens, I say retain no more than 3 decimal places, okay? So I give you lots of details. So let's begin by calculating the sample mean and standard deviation of these 5 weights, and we'll do that with our calculator. So I'm going to use my stat mode. Sorry, I'm going to use my data entry mode for statistics. I'm going to clear, so I have to clear work and start entering my value. So I'm going to enter 10.9, enter, scroll down to the X's, 12.6, enter, scroll down, 10.2, enter, scroll down, and 15.2, enter, scroll down, and 11.1, enter, scroll down. And now ask for the results, second stat. N is 5, X bar is 12, and S is 1.991. So N is 5, X bar is 12, and S is 1.991. Part B, calculate the standard error of the sample mean X bar. Okay, in other words, I would like to calculate the standard deviation of X bar. But because I don't know sigma, I have to use S instead. And when I do that, it goes from being called the standard deviation to being called the standard error. Needs a new name to distinguish between the population result and otherwise. So S is 1.991 divided by square root of 5. So the answer to the question of what parameter does the standard error approximate? It approximates the standard deviation of X bar, sigma over root n. So I'm going step by step, so you pull out the relevant statistics and values. The degrees of freedom is n minus 1 or 11. No, sorry, 4. So now construct 90, 95, and 99% confidence intervals for the true mean, which we don't know, and we don't know the sigma either. So we're going to use the formula x bar plus or minus now t star s over root n. Because we don't know sigma, we have to substitute with t instead of z and use s in its place. So all we really need, because we have x bar above, we've got s, and we actually calculated this to be 0.89. All we need is the t star. So let's put those numbers in. So this is 12 plus or minus t star times 0.89. And for 90%, t star is equal to what? 95% t star is equal to what? And 99% t star is equal to what? So what we need are the degrees of freedom. So we look at the right critical values on the table, right? So we go to T4. Now notice the upper tail probabilities are here. The critical value measures are below. How does the top margin relate to the bottom margin? Well, these are just half of the tail of the confidence interval measures. So I try and avoid confusion by just using, I try and avoid confusion by just using the bottom, going from the bottom. I don't know if that matters to you, but it helps me. So what I'm talking about is in this table, we want to work with T4. And I want 90, 95, sorry, now I forgot, 90, 95, and 99, okay? Those are all in the T table. So they're down here. So 90 corresponds to 5% in each tail, because it's 90 plus 5 and 5 is 100. 95 and 99. So I want this one, and this one. So I'll just make a note up here. So I want this one, I want this one, and I want this one here. It's hard to look at the both at the same time because this is way up here. So I want this critical value, this critical value, and this critical value. So it's easy when you know what you're doing, but can get confusing when you're practicing. So for 90%, the upper tail is 5. For a 95%, the upper tail is 2.5. And for a 99%, the upper tail is 0.005. So I can take that with me. Okay. And you can make each of the confidence intervals, and that's what I do. Okay. So let's test the hypothesis and let's go. So if you need to leave, you guys can go. I'll just finish this and put the video up. This is also, I describe this also in the lecture videos as well, but it's, again, it's not harmful to see it twice. So the dogs weigh 14 kilograms is going to be my status quo. And then I'm going to test against the alternative that they weigh less than 14. Okay, so this is less than, this is not a two-sided test. It's just a left-sided test. And yeah, I'm just going to continue solving. If you need to go, you should get going. Okay, so let's do this test together and then we'll call it a day. And then next week, I'm going to do the match pairs and just some exercises and the mock exam. Make sure the mock exam is open so you can start studying for preparing for the final exam. Well, I mean, you're preparing the whole time for your final, but I mean, literally doing old exams. All right, so for this problem, I need my information from the top, right? Let's set it up. So I'm going to test that it's 14 against it being less than 14. I'm reading that literally from the statement. I'm going to assume H naught is true. And what that accomplishes is that then I know that, well, actually, what I do when I do the T distribution, when I use it and I do the problems with sigma unknown, is I just do assume and assess together. Because otherwise it gets a little convoluted. So assess the evidence. I do them together and I say that T-stat is equal to my sample result, which was 12, minus its mean divided by its standard deviation. In this case, standard error. So remember, we have a hypothesized mean here. That's what I mean, the mean. So that's what I'm talking about. And then the standard error we calculated above. And when you put all that together, what do you get? So is 12 close to 14? Like, are they the same? Is our result of 12 similar or the same as the hypothesized 14? Well, I don't really know. I'm not very confident that I have a good feel for the T distribution. Never mind the fact that, you know, it's 4 degrees of freedom. I don't know that distribution very well. So I need to do this calculation to check how many standard deviations I'm away from the hypothesized value. And I get, let me double check. So it's 12 minus 14 divided by 0.89. And I get negative 2.247. I can keep 3 decimal places because my table has 3, the T table has 3. If it was for the Z table, I just keep 2. Right. And then what do I do? So I've done my 3 steps. Now I'm going to, this doesn't have to take a long time, right? Now I'm gonna calculate a p-value. And the way I do that is I make a drawing and I put T4 and I plot my test statistic. and I look at about the probability of being there or more extreme according to this sign here. So then I look here and I try and find out what that value is. We know how to do that, right? Because we learned all about the t-distribution just now. So let's actually have the table up here. Is this going to be helpful? So 2.247 is between these two. 2.247 is between these two on the right side, but it's the same if they're negative. So it's between 2.5% and 5%. You guys can ponder that. So that's going to be between 2.5% and 5%. And how do we conclude? Always the same statement, p-value less than or equal to alpha means reject H naught. The p-value is between, now you can go into Excel and get the right answer, but just doing it with the table. You agree that between 2.5 and 5% is smaller than or equal to 5%. So that equal really comes into play, right? In this case, you do reject H naught. So it means that we have evidence that the weight is less than 14 kilograms. Very good. All right. So you guys can check out the answer. The test is significant and continue studying. You know everything you need to know for the final exam. Now it's just a matter of practicing. You have any questions for me before I close out? So you're going to have to learn the matched pairs, which is basically the same test, but just read through it and try some exercises, do all the exercises you can that remain, and we still have 2 weeks to the final. So you guys are in good time. Go back if there's things you don't understand. I think you have all the resources at your disposal. So 1, 2, wow, it's 3 weeks still. So we have lots of time to review and prepare. I put up a Connect quiz. I'll put another Connect assignment, and I'm going to drop like the worst Connect assignment, or maybe 2 of them if we keep going with the Connect assignments. Okay, so take care. I'll put up the video and have a good week. Oh yeah, happy Father's Day to all your fathers, or if you're a father, Feliz Día de los Padres.